Ah, for the good old days. Wasn't that a beautiful Model T? And then again, wasn't that a beautiful Corvette? It all depends on your point of view. One thing is for sure, the old cars were easy to repair. Well, things have changed. Added conveniences and government regulations, anti-skid and airbags, four-wheel drive and four-wheel steering, even environmental temperature control. The method? Electronics, computers, the little black box. The Corporate Training Department of Standard Motor Products presents this video training program as part of our continuing effort to keep you up to date on how to repair today's cars and remain profitable. This high-grade fuel systems training module covers the Ford Motor Company port fuel injection system. In order to competently and profitably repair this system, the mechanic must have certain hand tools and test equipment. Also, he should have a working knowledge of the basics of fuel injection and have an understanding of the Ford electronic engine control system. He should also be familiar with the concepts of open loop and closed loop. And most important, he should be familiar with electrical and electronic diagnostic procedures. Before we actually begin working the Ford system, what is it trying to accomplish? What does each of the components do? And how do they interact with each other to affect the overall operation of the vehicle? You should keep in mind that the main purpose of the engine control and fuel system is to allow the vehicle to give good fuel mileage and meet the federal emission standards, but not at the expense of good acceleration and smooth operation. Let's take a closer look at the system and the components. From your basic knowledge of fuel injection, you should also recall that a fuel injection system can be broken into three main parts: the air management system, the fuel control system, and the influence of the engine computer control system on fuel and air delivery. Through the proper operation of each of these subsystems, the vehicle can meet all of its design objectives. You should recall that the best operating compromise for a gasoline engine is to control its air and fuel ratio in a very narrow operating range. In fact, as close to 14.7 parts of air to 1 part of fuel as possible. Everything the injection system does is designed to meet the federal standards of mileage, emissions, and still give good drivability. Ford uses two different types of port fuel injection. One is a mass airflow style. It is utilized on the 1.6, 1.9, and the 2.3-liter turbo engines, and on the later 5-liter high-output engine. The second style is a speed density type found on other engines and vehicle combinations. Ford uses two different sets of components to derive the mass airflow calculation for the engine control computer. One airflow sensor is the vane meter style, and a second type, primarily found on the 5-liter high-output engine, is a hot-wire mass airflow sensor style. This is similar to the type used on Nissan and General Motors vehicles. Since we will be repairing a Mercury Marquis during this program, let's look at the fuel system components. You can see that this Mercury Marquis has a 5-liter V8. The components in the air management system consist of the air filter and duct assemblies. The throttle body assembly contains a single butterfly. In some cases, 2 butterflies are used to control airflow into the engine. Also notice that the throttle body assembly contains cooling lines to circulate engine water around the throttle plate assembly and the ISC unit. The ISC is an idle speed control assembly, bolted on the back side of the throttle plate unit. To direct the airflow into the cylinder, Ford uses a set of tuned ram pipes. They may be pretty, but are difficult to work around, as you will see. The fuel management system on this vehicle consists of an electric fuel pump mounted inside the fuel tank and a very fine inline fuel filter. The pump's output travels to the fuel rail and then to each of the individual injectors. To maintain fuel pressure in the system at a specific level, a fuel pressure regulator is mounted on the outlet side of the fuel rail. Unused fuel is then allowed to pass through the regulator and return to the fuel tank. The fuel pressure is maintained in the fuel rail at between 35 and 45 pounds per square inch. You should note that Ford does not utilize a cold start injector on any of their engines with multi-point fuel injection, except the Ford Probe and the Mercury Tracer. These vehicles are actually Mazda 323 and 626 vehicles. A separate video program titled Mazda Electronic Fuel Injection covers diagnostics and repair procedures on the Ford Probe and the Mercury Tracer, and Mazda Electronic Engine Control System, which discusses diagnostic procedures on the electrical portion of the Probe and Tracer vehicles. Remember, when working on these cars, that they do not utilize the Ford EEC system. Though many different engine configurations exist, 4-cylinder, inline-6, V6, and 8-cylinder, the basics of the Ford Motor Company EEC and sequential or port fuel injection systems are the same. Just remember that there are two different styles, a mass airflow system and a speed density system, and that the engine control assembly uses different sensors to calculate pulse width in each of these systems. You should remember that the injector pulse width is only a measurement of time the injector is open, and the time can vary from 2 milliseconds for a very lean mixture to 40 milliseconds for a very rich mixture. Ford controls injector discharge in the 4-cylinder engines by turning on all the injectors simultaneously each crank revolution. Some V8 engines use a sequential method, or SEFI, to control the injector time separately for each cylinder. In 1985, 6 V6 and V8 engines, except the 5-liter HO engine, the injectors are fired in groups of 3 or 4 each engine revolution. Then the opposite 3 or 4 are fired on the next engine revolution. For these systems to operate effectively, numerous sensors interact with the engine control computer to supply it operating information. Since we have two different systems, let's look at each separately. Details of the engine control assembly in a speed density system show that the ECA receives sensor input information from a TP or throttle position sensor. It supplies information on throttle position and rate of throttle change. The MAP, or manifold absolute pressure sensor, which measures manifold pressure or vacuum. The ACT, or air charge temperature sensor, which supplies inlet air temperature in the intake manifold. The EGR valve position sensor. The HEGO for heated or non-heated exhaust gas oxygen sensor, which signals the quantity of O2 in the engine's exhaust. An ECT engine coolant temperature sensor, and a PIP, or profile ignition pickup sensor. This signals cylinder position and RPM. Also, a series of miscellaneous switches. These could include idle tracking switches, air conditioning compressor clutch switches, or even an electronic fan controller assembly which interacts with the electronic fuel injection system, including supplying a power path to the fuel pump itself. Lastly, an input from a NOx sensor is found on many applications, particularly turbo engines. If the system is a mass airflow system, we would still use its throttle position sensor, the EGR valve position sensor signal, the ECT signal, and the PIP signal. But instead of the MAP and ACT input, the ECA would receive information from a vane meter or hot wire MAF sensor. These supply a calculation on the amount of air entering the engine. Also, the MAP would be replaced by a BP or barometric pressure sensor. Simple. Don't be confused by all the different components and sensors. All you need to be able to do is recognize the components by sight and understand their function. Normally, all turbo engines utilize the vane meter assembly. That is, the 1.6, 1.9, and 2.3-liter turbo engines. On the 5-liter high-output engine and some 89 vehicles, you can look for the hot wire mass airflow sensor in the inlet duct. On the supercharged 1989 Thunderbird, you will find a MAF sensor. Don't forget, on turbo and supercharged applications, a knock sensor is utilized to control the timing function. Next, let's take a closer look at the output of the ECA. The computer utilizes the input information, performs its calculations, and determines a strategy for the output information. The output is used to control the various functions of the engine to meet emission and fuel standards. The ECA controls the fuel injectors. This is done by switching the ground path for the injectors. It controls the emission control system consisting of the EGR valve itself and the air pump or thermactor air bypass assembly. It also controls the evaporative emission control and the idle control system, which primarily consists of the throttle air bypass solenoid. Of all the different sensor inputs to the computer, our concern during this program will be limited to only those that affect the fuel system. Of these, you should keep in mind the ECT, ACTMAP, BPMAF, TP, and PIP influence the ECA to control the primary pulse width calculation in closed loop. Don't forget that the ECA output drivers merely complete the ground path for the injectors, and that the on time of the injectors is the pulse width, and therefore directly affect air-fuel ratio. Closed loop or feedback functions with these sensor inputs that control primary fuel injection pulse width. The outcome of the combustion process, exhaust, passes by the oxygen sensor, EGO, and fine-tunes the computer and the resulting pulse width. A second mode of operation is called open loop. During this mode of operation, the above sensor information, including information from the oxygen sensor, is not utilized by the ECA. During this mode of operation, the computer operates using internal memory and pre-established programs to control injector pulse widths. As a point of information, you should keep in mind that as the oxygen sensor voltage increases to a higher reading close to 1 volt, it shortens the injector pulse width to correct for a rich reading. And obviously, if the fuel mixture is already too lean, the injection pulse width will widen, requiring more fuel. If any of the components malfunction, or if a bad O2 reading is received by the ECA, the computer has the capability of substituting default values or switching to open loop operation and running on its programmed memory. Let's take a look at a few of the components before we go into troubleshooting. The hot wire mass airflow sensor is similar to that utilized by General Motors and Nissan. As the air enters the engine through the air filter, it passes across a heated wire. Obviously, as the air passes by, it draws off the heat. As the wire is cooled, more electrical current must be passed through the wire to maintain the temperature. The electrical current flow through the wire is calculated by the ECA assembly. This data is converted to a frequency signal, which is then utilized by the engine control assembly to calculate the mass of the incoming air and complete the pulse width calculation. The MAF, or mass airflow sensor, is non-repairable, non-adjustable, and basically non-serviceable. If it malfunctions, it will have to be replaced. This vane airflow meter is typical of those utilized by most import vehicles. As the air passes through the engine, it passes by a temperature probe, or inlet air temperature sensor. Entering air also passes by this door. The door moves in response to the volume of the air. The door is connected to a potentiometer. The potentiometer moves, supplying a voltage signal to the computer, which indicates the amount of the incoming air. The air volume and temperature together supply the information to calculate the mass of the air. Very simple. The only problem is that the units are prone to dragging or binding, which ultimately affect the air calculation. For all practical purposes, this unit is not field serviceable, though rebuilt units are available. If the door binds or the unit goes out of calibration, it must be replaced. Engine coolant temperature sensors, charge air temperature sensors, ambient air temperature sensors, etc. are all thermistors. That is, the sensors change resistance with temperature. Their output signal is a variable voltage signal. The range is typically 0.3 volts to 4.5 volts. The TP, or throttle position sensor, is also nothing but a variable resistor, though not a thermistor in this case, and not a wire-wound resistor. It is a carbon resistor. It also supplies a variable voltage signal to the computer with a change in resistance of between 0.5 and 5 volts. In most all applications, except 1988 and newer vehicles, the throttle position sensor is non-adjustable. If it malfunctions or is out of voltage range, it should be replaced. The MAP, or manifold absolute pressure sensor, converts manifold air pressure to a digital voltage signal of a varying frequency. It is actually comprised of a pressure-sensitive metal disc that functions as an electrical capacitor. The sensor is connected to manifold air pressure by a vacuum hose. As manifold vacuum or manifold pressure in the case of a turbo changes, the input signal to the MAP sensor changes. The output to the ECA is ultimately a variable frequency signal of normally between 92 and 162 Hertz. Basically, the higher the manifold vacuum, the higher the frequency signal. That's it. We have covered the basic components and functions of Ford systems. Now, let's repair this Mercury marquee. I know that hands-on experience may be the best teacher, but through the use of video, we can simulate almost everything except your hands actually touching the components. Ready to begin working on Ford fuel injection? The customer's complaint has been hard starting, and today it won't start at all. The first problem is deciding whether the condition is fuel-related or ignition-related. Obviously, it could be any number of things. You need to follow a logical approach to troubleshooting. The first step to a successful repair is to derive some general information, particularly the VIN code and the exact details of the complaint. Remember, you are looking for the 8th and the 10th digit. Don't make an error. Double-check the VIN code digits. The 8th digit indicates the engine type and make, and the 10th indicates the exact year. Whatever you do, don't guess. Always ask the customer the questions necessary to determine exactly what his complaints are and when they occur. Remember, you cannot diagnose a problem that doesn't exist. Next, do a visual inspection. Check the spark plug wires, the air filter, the battery terminals, and voltage output of the charging system, the coolant level and antifreeze quantity. Check the operation of the engine's cooling fan. With the necessary information in hand and the visual inspection complete, we need to isolate which system is causing the problem. This can be accomplished using either an engine analyzer or handheld test equipment. The first step in the repair of the vehicle is to check for spark. In other words, split the ignition and fuel systems. This can be performed quite simply by utilizing a spark tester to replace the spark plug. Since this program deals specifically with fuel injection and related problems, we do have spark and will therefore eliminate the ignition system and the emission systems from the remainder of this program. Any number of steps can be taken next. You can follow a symptom troubleshooting chart. You can use a Ford H manual or a comparable manual, and you could go off and make assumptions based on prior repairs. But let's follow a step-by-step test procedure designed around the original Ford test sequences. One simple test that can be performed to verify if fuel is available to the injector is to check the fuel pressure to the engine from the tank. This test can be performed by merely connecting a fuel pressure gauge to the test port mounted on the fuel injector rail. You should note that on other engines this is not such an easy task and may require using adapters to hook up the gauge. The test connector is a Schrader valve requiring the proper adapter on the test gauge hose. Once installed, turn the ignition key on and off 3 or 4 times slowly. Remember, the fuel pump will only run for a few seconds after the key is turned on. If the engine doesn't crank and start, the pump will stop. No fuel pressure. You should always check for fuel pressure with a gauge, since it is very difficult to hear the fuel pump run, since it is mounted inside the fuel tank. What could cause the pump to not supply pressure? Since this vehicle was just transported into the shop on a wrecker, quickly check the inertia switch. In this vehicle, it is located by the left trunk hinge. The white button is in the up position. This was most likely triggered when the vehicle was being transported in an other than normal attitude. This safety switch is common to all Fords and can be triggered accidentally by luggage in the trunk or even when closing the trunk hard. Push the button down and reset the switch. Turn on the ignition key. The pressure is at the specified point. Now, monitor the gauge to assure that the pressure maintains with the key off. It should stay at between 35 and 45 pounds per square inch without a pressure drop. Good. We know we have spark. We have fuel pressure supplied to the rail. Let's try to start the engine. Still a no start. Here is where the testing can get extremely tricky. To illustrate this point, we will lead you through a symptom-generated test sequence and pinpoint test first, and show you the possible consequences. Consulting a symptom chart on diagnostics, look up instructions for no start condition. Let's go directly to the portion of the test which checks the fuel system. This test procedure is easily done by connecting a Noid light to one of the injectors, then cranking the engine to determine if the injectors trigger. This test can also be done with a breakout box. Utilizing a 12-volt test lamp, connect the test lamp between pins 37 and 58, which go to one of the fuel injectors. Crank the engine and note if the test lamp lights. Ford's test states that if the lamp does not glow on either of these tests, verify battery voltage to the computer, actually to the fuel injectors. If power is available to the fuel injectors and yet the injectors do not pulse, replace the ECA. In other words, we are to change the engine computer because fuel pressure is available to the injectors, we have power to the computer and to the injectors, yet no power or path to ground. Remember, the computer injector drivers supply the path to ground to pulse the injector. But during this procedure, we would change the computer and find out that the engine would still not start. Next, let's look at the Ford key-on, engine-off quick test and follow that procedure to derive the correct repair for the vehicle. During this test, you can utilize a Ford Star Tester, a simple analog voltmeter, or any of the aftermarket scan tools available. In some instances, even the dashboard indicator light or check engine lamp can be used for trouble codes. To perform a key-on, engine-off test, Ford recommends doing a quick visual inspection, then set the parking brake. Place the transmission in park or neutral in manual transmissions. Turn off all electrical loads such as radio or air conditioning, and make sure that the doors are closed. Always check coolant level and antifreeze quantity. Turn the ignition key to the off position. Connect the scan tool or an analog voltmeter to the vehicle's self-test connectors. If you are utilizing an analog voltmeter, connect the positive voltmeter lead to the positive battery terminal. Connect the negative voltmeter lead to pin 4. Install a jumper wire from the single pin connector adjacent to the multi-pin self-test connector to pin 2, or the signal return pin. Set the analog voltmeter to a DC voltage range of approximately 15 volts. Using the scan tools requires you to plug the tool into the diagnostic plug per the tool manufacturer instructions. Then program the scan tool with the requested information. This varies by tool manufacturer. Normally, certain VIN code information and answering various questions will complete the process. Turn the ignition key on to initiate self-test. Do not touch the throttle during the key-on, engine-off test. Observe and record all code numbers if you are using a scan tool, a dashboard indicator light, or count the needle deflections on the analog voltmeter. A code 23. A 23 refers to a problem with the throttle position sensor. But what type of problem? Due to the design of the Ford throttle position sensor, it is recommended that you do not utilize an ohm meter to do a quick resistance check of the throttle position sensor. sensitives of the carbon wiper variety, you can get an erroneous reading. By this time, I'm sure you're wondering, what in the heck does the throttle position sensor have to do with a no-start or an intermittent no-start condition? It controls the signal to the computer that enters into the pulse width strategy. Remember, the change in voltage from the TP sensor ranges from about 0.5 to 5 volts. It signals rate of throttle change, idle, or wide open throttle. What do you do when the car is flooded? You get in the car, put your foot totally to the floor, and turn the key. The throttle plates are wide open. Maximum amount of air rushes through, and when the air-to-fuel ratio is correct in the cylinder, the spark will ignite the mixture. The vehicle will start. In a fuel injection system, the same situation exists. The electrical engineers designed the clear flood mode into the throttle position switch and the map sensor. This is the only mode in which zero fuel is allowed while the engine is running or cranking, clear flood mode. It is triggered by the throttle position sensor, in this case, not the engine control computer. How do we verify this? Utilizing a digital volt-ohm meter is the best method, or at least a very high impedance analog voltmeter. Measure the voltage supplied to and across the throttle position sensor. Unplug the TP sensor harness. On the black and orange wire, we should have 5 volts to ground. This is the reference voltage supplied by the ECA. To test the circuit effectively without a breakout box will require taking the harness plug apart. To perform this test, it will be necessary to back probe the throttle position sensor while it is plugged into the engine harness. Check the voltage across the throttle position sensor and the voltage supplied by the wiper arm. We have an open circuit. We are reading 4.8 volts. This is a signal to the computer for wide open throttle. Obviously, the carbon wiper or the carbon pickup is cracked. This could happen as an intermittent problem, or in this case as a continuous problem. The computer thinks that the throttle is wide open, even though that is not the case. Replacing the throttle position sensor is a simple matter of removing 2 screws. This is a non-adjustable unit. Simply install a new unit and bolt it in place. Reassemble the harness and start the engine. Doing a complete visual inspection, splitting the system into either ignition or fuel, and utilizing the key-on, engine-off test will always lead to a successful repair. It may not seem easy, but very few problems pass the key-on, engine-off test. If they do, the remainder of the problems will be picked up or isolated with the key-on, engine running test. As you can see, working on Ford is not difficult if you follow a logical approach to troubleshooting. But remember, if you skip steps, you can end up in a situation like this one, replacing the engine control computer assembly and still not repairing the vehicle. I would like to take this opportunity on behalf of Standard Motor Products, its high-grade division, and its training department to thank you for purchasing this training program. And we hope you will consider us for your future replacement parts needs.